Okay, so now we move to the next chapter, chapter 7, the normal distribution. Okay, so when it comes to the normal distribution, actually, we will be using the normal distribution to work with continuous data. So if you recall the previous chapter, in the previous chapter, we worked with discrete data, right? So we worked with the discrete distribution. So now in chapter 7, this normal distribution is specifically used to model continuous data, only continuous data. Okay. So they say here a continuous random variable has a continuous probability distribution, right? So if it is a continuous variable, it should have a continuous probability distribution. So you need to identify now. You need to recall that continuous variables, they can take any value in a given range, right? Now in discrete, you could only take specific values. It doesn't take every x value, but in continuous, you can take any value in a given range. So then they are saying when it comes to these continuous probability distributions, like okay, when it comes to continuous variables, and if you try to take this continuous variable into some kind of a distribution, it always comes as a curve on a graph. It doesn't come in a table. In the previous section, do you recall we drew each x value, we drew the probability. For x, you write the probability. That's what we did, right? It was a simple table. The probability distribution was simply a table. But now in continuous distribution, the probability distribution is not just a table because it's not possible to write the x value and the probability, right? Is it possible to write the every single x value and its corresponding probability? No, you know that x values come in a range, and when you come to x values in a range, there are infinite amount of numbers. When you come to a range, you can write. So let's say you are modeling the weight. If you are modeling the weight, okay, so then you can write. I mean, you can get any value in a given range, which means there are so many x values that you can't simply make a table here. Do you understand? It's not possible to make a table with a few set of x values. That's why continuous distributions must be modeled using a curve. You need to draw a curve to model this. Okay, so they say here a continuous random variable has a continuous probability distribution. This can be shown as a curve on a graph. It has to be shown as a curve, the probability distribution. Okay, and then you recall in the previous chapter when you drew the table for the probability distribution, the total probability was what? Always the total probability adds up to 1. The same story here. If the probability distribution for the continuous random, if the continuous variable is a curve, then they say the area under the continuous probability distribution curve must be equal to 1. Basically, the area under the curve gives the probability. So these are the important things you need to understand. So we will go into more deeper context. So at this point, just take these points. Okay, we will go into more deeper context. We will draw the graphs, and I'll be explaining you in much deeper context. Okay, at this point, so basically the main thing that you need to understand here is continuous variables are modeled by the probability distribution must be a curve. So examples of continuous variables that can be modeled using the normal distribution. Okay. Okay, wait. They are saying here the normal distribution is a continuous probability distribution and can be used to model many naturally occurring characteristics that behave in this way. Okay, and also they say the continuous variables generally encountered in real life are more likely to take values grouped around a center value than to take extreme values. Okay, so this is kind of important. What they're saying is when it comes to real life, okay, data are more tended to group around a central value. What do you call the central value in a data set? Kind of like the central value. We can say it's the mean, right? Right, so mean is like the mostly used average that best represents the whole data, and you can see, and if you recall, do you recall the variable called standard deviation? What does standard deviation do? It measures how spread the data is around the mean. Do you recall in chapter 2? So the mean is kind of like a central value that gives like the central value of the data, and the standard deviation shows how much the data has spread around the mean. Okay, so what they're saying is in real life, they say data is tended to be more grouped around a central value. So if the mean, the data is more grouped more closer to the mean than at that extreme. I mean, if you go further away from the mean, you will have lesser amount, lesser. Let's say you have lesser data points. Okay, so around the near closer to the mean, you have more data points. Okay, that's what they're saying here. So examples of continuous variables that can be modeled using normal distribution are heights of people within a given population. So if you take heights of people, you will see that more people are grouped around a certain height limit. So you will find a lower number of people who are extremely short and a lower number of people who are extremely tall. So most of the people would be in a height within a central mean value. Most of the people would be near the mean value, while lesser people are distributed away from the mean. Do you get it? So weight and then errors and size variations. So they've given you some examples. Okay, so now let's see how to model the normal distribution, how to draw the curve, and how to find probabilities using normal distribution. Okay, so you can see over here below, they're explaining, you can see the description. Now you can see the distribution becomes bell-shaped. So we were discussing about the normal distribution, and I was saying you that it becomes, you have a curve, right? You have a graph. So the graph, the distribution, the probability distribution becomes bell-shaped and is symmetrical about the mean. I think you can see this graph here. Do you see? So the graph, you get a bell-shaped kind of graph, and this graph is going to be exactly symmetric around the mean. So you can model the height of adult males in this city using a normal distribution. So as I told you previously, now for example, they've taken the height here, and you can see most of the people are closer to the mean height. You have very few people who are like extremely short and few who are extremely tall. Do you see? So most of the people are centered around the mean, most of the data points. So they are saying to be a normal distribution, the data must be symmetric. Symmetric means what? You have like 50% of the data behind the mean and another 50% of the data after the mean. Are you with me? Okay, so these are really important thing here. Look, the normal distribution has parameter mu. Mu is called the population mean, and sigma square is the population variance. Okay, so these are the two main parameters we use in a normal distribution, the mean and the variance. Then the next important thing about the normal distribution is it is symmetrical. So what do you mean by a symmetrical? Okay, so symmetrical graph means where the mean is equal to the median and it's equal to the mode. Mean, median, mode, all three are equal. That's called a symmetric graph. Okay, and then the next one is it has a bell-shaped curve. So there's a bell-shaped curve with asymptotes at each end. Can you see at each end that you are reaching closer and closer to the x-axis and you are making an asymptote over in this end. So that's what they say, has a total area under the curve equal to, has a bell-shaped curve with asymptotes at each end. At either end, you have an asymptote. And then they say has a total area under the curve equal to 1. So the total area under the curve must be equal to 1. Are you with me? The total area under the curve must be equal to 1. And then they say has points of inflection at mu plus sigma and mu minus sigma. Okay, so points of inflection means where the curve kind of becomes, how do you say, the gradient kind of becomes 0, right? So the points of inflection, these points over here are at mu plus sigma and mu minus sigma. Okay, and then let's move on. There are some important things you need to know here. For a normal distributed variable, they say approximately 68% of the data lies within one standard deviation of the mean. So what does this mean? What does this mean? So if I draw a normal distribution, okay, so this is extremely important. So now we know how the normal distribution looks like. Am I correct to say, it's a bell-shaped curve? It's a bell-shaped curve. Try to draw a symmetric curve. And it is centered around the mean. Do you agree? It's centered around the mean. Okay. The total area under the graph is 1. Okay. And they are saying for a normally distributed variable, approximately 68%. Now, total area under the graph is 100%. So this is out of that 68% of the data lies within one standard deviation of the mean. What do you mean within one standard deviation of the mean? So from mu, if you go 1 sigma forward, mu plus 1 sigma, and if you go 1 sigma behind, can you see? So if I draw this line over here, they are saying between mu plus 1 sigma and mu minus 1 sigma, how much data points do you find? There is 68%. 68% of the data will be between mu minus 1 sigma to mu plus 1 sigma. Are you with me? Okay, and then if I just ask you how much of the percentage data do you have after mu plus 1 sigma? So if I ask you this question, what is the probability that let's say our continuous variable is x that x is greater than mu plus 1 sigma, what would you give me the answer? Now we know this distribution is symmetric, right? So from mu, if you go 1 sigma forward and 1 sigma behind, you are covering the same. I mean, you have gone an equal distance to both the sides. So then what you could do is from 100%, you subtract the 68%. From 100, when you subtract the 68, you get the area of the remaining two parts. How much is it? 32%. So 32% is the area of the remaining two parts. Then we can divide it by, now you know these two areas must be the same because the graph is symmetric. Remember the graph is symmetric. So then if you divide that by 2, how much each side gonna be? This is gonna be 16%. Can you guys see? This is going to be 16%. So this area that x is greater than mu plus 1 sigma is going to be 16% or 0.16. Or even if you take the probability that x is less than mu minus 1 sigma, that is also 16% or 0.16. Are you with me? And also the next one, for x within 1 standard deviation of the mean, you have 68% of the data. Is this clear? One more thing I should ask you is, what is the probability that x is, let's say, greater than mu only? Just to ask you, what would be the probability that x is just greater than mu? Now mu is exactly in the middle, right? Which means what? If it's exactly in the middle and it's symmetric around mu, the total is 100%, which means just to one side greater than mu means you only take this section, right? Greater than mu means only this red color section. Do you see? So how much area do you think we are covering then? We will be covering 50%. So just you should know these things. Okay, so that's 50%. And then we'll continue to the next point. So these are some important things. Then they say 95% of the data lies within 2 standard deviations of the mean. Do you see this point? What are they saying? Now, in the previous one, they said 68% of data lies within 1 standard deviation. So you will find 95% of the entire data set within what? Within 2 standard deviations. So if I show that on the diagram, how does it work? So within 2 standard deviations mean, this is the graph. So this is the mean. So you can see they are saying that within 2 standard deviations, you will find how much data? 95% of the data will be within 2 standard deviations. Do you see? So between mu minus 2 sigma to mu plus 2 sigma, you will find 95% of the data in between these two. Is this clear? Okay, so these are some standard rules that are given to you. So what if I ask you the probability that x is greater than mu plus 2 sigma? What would be your answer? So I think you can see that mu plus 2 sigma is just this part that's outside, right? How do I get that area? So I think you can see the graph is symmetric around mu. That's why, so mu plus 2 sigma, mu minus 2 sigma are equally spaced around mu. So what you should do is from 100%, you subtract 95% and that gives you 5%. The 5% comes for both the sides. Do you see 5% comes, the remaining 5% is covering both of these sides. So we should divide that by 2. So how much do you get? 2.5% or 0.025. Is this clear? So x greater than mu plus 1 sigma, mu plus 2 sigma, or even x less than mu minus 2 sigma. Guys, can you see? Mu minus 2 sigma is this. So x less than mu minus 2 sigma is also 2.5%. And the main thing they want you to tell here is that x is greater than mu minus 2 sigma and less than mu plus 2 sigma is 95% or 0.95. Okay. And then the next point you can see nearly all of the data. 99.7% lies within 3 standard deviations of the mean. So if you go 3 standard deviations of mu plus 3 sigma to mu minus 3 sigma, you're covering like the entire, most of the data points are covered by the time you reach 3 standard deviations. Is this clear? Okay. Okay. Okay, so now we'll move on to exercise 7A, question number 1. Okay, so state with the reason whether these random variables are discrete or continuous. So part A, they have said capital X, the length, so the length of a random sample of 100 snakes. Okay, so basically, the important thing is we are describing our data, the main thing that we are measuring here, the random variable is the length. So the length, when it comes to the length, length is a continuous random variable. Okay, so first one part A, answer it's a continuous random variable. And why should it be continuous? Continuous variables take any value, right? So length can take any value. Length could be any, it could be, it doesn't take specific value. So you can say length can be any value. That's the reason it is continuous. Part B, why? So why the scores achieved by 250 students in a university entrance exam? So when it comes to the exam results, are you capable of getting any value or do you get only specific value? And say when you get marks, you get like so when you get marks, you get these specific values, right? You can't get like any amount of decimals for the marks. That's not how it works, right? So you go with 1, 2, 3, 4, 5. You take those specific values, isn't it? So in that case, marks are definitely discrete. And you can say why the exam scores can only take only specific values. It doesn't take every value. Okay. Then next one, see the masses of honey badgers in a random sample of 1,000. The main thing we need to think here is it's the mass. So mass is definitely a what variable? Mass is a continuous variable. And what's the reason? Mass can take any value. Mass can take any value. And part B, give the shoe sizes of 200 randomly selected women in a particular town. So the shoe size, when it comes to shoe size, you don't have every value, right? You only have specific sizes. The shoe sizes are specific. You have those sizes that are given. So those are the values you can take. So shoe size is definitely discrete. Shoe sizes take only specific value. Is this clear? Okay, so then we'll go to question number 2. Okay, here they say the lengths capital X millimeter of a ball produced by a particular machine are normally distributed with mean 35 millimeter and standard deviation 0.4 millimeter. Sketch the distribution. So how do you sketch the distribution? So when you sketch the distribution, it's a bell-shaped curve. It's a bell-shaped curve and it's symmetric, isn't it? Now that's one of the key properties of a normal distribution. It must be symmetric around what? Mean. The mean is 35. And the standard deviation is given to you as 0.4. So standard deviation shows how spread the data is around the mean. So I think what we can do here is we could say, now, they gave us a specific rule in the previous part, right? So we learned here that approximately 68% of data lies within one standard deviation of the mean. 95% of data lies within two standard deviations. Shall we find that as well? Okay, let's get the values of mu plus 1 sigma and mu minus 1 sigma. So mu is 35, right? 35 plus 1 sigma. How much is 1 sigma? Standard deviation is 0.4. So 1 times 0.4. How much is it? 35 plus 1 times 0.4 is 35.4. Do you agree? The other guy is 35 minus 1 times 0.4. How much is it? Get the answer? So that's 34.6. So then what can we say here? We can say that how much percent within one standard deviation you have 68%, right? So you can say 68% of the data. You can say here 68% of the data, okay, lies within lies within 34.6 millimeter. This is in millimeters, right? We are getting the length 34.6 millimeter to 35.4 millimeters. So these are some extra things that we are calculating here. Okay. And also, shall we get the 95% also? So mu 95% of data lies within two standard deviations. Let's get that also. So mu minus 2 sigma and mu plus 2 sigma. Mu is 35. 2 times sigma is 0 0.4. 35 plus 2 times 0 0.4. How much is it? 35.8 millimeter. No, mu minus 2 sigma, right? This is 35.8 millimeters. 34.2 millimeters. So then what we say here, we can say 95%. 95% of the data lies within 34.2 millimeter to 35.8 millimeter. Is this clear? Okay, and one important thing here that we need to also know, now when it comes to the normal distribution, you can write it in this manner, the parameters. So we write like this, x follows, so this looks really new to you. This is a completely new notation. Okay, so x follows a normal distribution with mean mu and variance sigma square. This is actually a standard notation we use to denote that a variable follows a normal distribution. So you can write here x follows. So this mark means the data is following. Over here, a normal distribution, our mean was 35 and our sigma value, our standard deviation was 0 0.4, right? So sigma square means 0 0.4 square. So this is actually a standard notation. So whenever you see that they give a variable with this particular sign, you must know the first thing they write here denotes the mean. The second thing they write here denotes the variance. The sigma square, it's the variance. Okay. So this also is something that you need to know. Okay. So let's move on to. Okay, this is simply saying that the x follows a normal distribution. That's all. Okay, that it doesn't mean anything more, but from this you can immediately extract the mean and the variance. Sometimes they would not give it to you in the question, they will just give it to you in this manner. So this is a standard notation. Okay. Okay, we'll go to question number 3. They say the data, the distribution of incomes in thousands of dollars per year of employees at a bank is shown on the right. State with reasons why the normal distribution is not a suitable model for this data. So why is the normal distribution not suitable? I think when you look at this graph, one main feature, immediately you can see that a main feature is missing. What is it? In a normal distribution, the data must be symmetric. So you can see clearly here, this graph is not symmetric, right? So that's the reason. So you can write the data is not symmetric around the mean. Therefore, this cannot be a normal distribution. So something you need to just explain it. Okay, so the bank's income, the employee's income is not distributed symmetrically around the mean value. Therefore, this is not a it's not suitable to be modeled by a normal distribution. Okay, so I just said the answer now. All right, so let's go to question number 4. The arm spans of a group of year 5 students, capital X centimeter, can be are modeled as X. Can you see this? X follows a normal distribution. And I told you, when you see this, what does this represent? Now they have written here X and this mark normal distribution. They have written here 120 and 16. Okay, so the moment you see this, you should know the 120 represents what? Normally, this is the mean and this is the sigma square. So 120 represents mu and the sigma square represents the, sorry, 16 represents the sigma square. Is that clear? Okay, they are asking you state the proportion of students who have an arm span between 116 and 124. So they are asking you the percentage. Proportion means the percentage, the probability. Okay, I think we'll try to find the values of mean minus 1 sigma and mean plus 1 sigma. First of all, what's the sigma value before we go for the value? You can see sigma square is what you have as 16, right? So which means the standard deviation is root 16, which is 4. Okay, so now let's get the value of mu minus 1 sigma and mu plus 1 sigma, because we know that 68% of the data lies within minus 1 sigma and plus 1 sigma, right? So mean is 120 minus 1 times 4. 120 plus 1 times 4. 120 minus 4 is 116. 120 plus 4 is 124. I think you can see. State the proportion of students who have an arm span between 116 centimeter and 124. So what's the proportion? 68%, right? So you can say 68% of the pupils. Pupils have an arm span within 1 standard deviation of the mean, within 1 standard deviation of the mean. So part A is done. Part B. State the proportion of students who have an arm span between 112 and 120. I think you can see the range just became large, right? Previous was 116 to 124. Now it became 112 to 120. You can see both sides. The range has, I mean, 116 has dropped to 112. 124 has dropped, has increased to 120. The range has increased. So maybe we could try with mu minus 2 sigma and mu plus 2 sigma. And what was the rule? Within 2 standard deviations of the mean, how much data percentage do you find? 95% of the data lies normally within 2 standard deviations of the mean. So mean 120 minus 2 times sigma is 4. 120 plus 2 times 4, how much is it? 120 minus 8 is 112. 120 plus 8 is 120, and you can clearly see, right, and between 112 and 128. So you can write here 95% of pupils have an arm span. Arm span is the variable here. Within 2 standard deviations. Ninety-five percent of pupils have an arm span within 2 standard deviations of the mean. Okay. Okay, so next I'll move on to question number 5. The lengths of a group of snakes y centimeter are modeled as y follows a normal distribution with mean 100, variance sigma square. If 68% of the snakes have a length between 93 and 107 centimeters, find sigma square. So how do you do this? We know that 68% of the data will lie within what? Will lie within 1 standard deviation of the mean. So I think you can clearly understand here in the 5th question that 93 should be what? So they are saying 68% of the data lie between 93 and 107. So 93 should be the mu minus 1 sigma and the 107 should be the mu plus 1 sigma. That's how it should be. And I think you can see here they have given you that the mu value is what? Mu value is 100. So mu is actually given to us. So we can work with one of the equations. I'll work with 93 equal mu minus 1 sigma. 93 equal mu is 100 minus 1 sigma. So 1 sigma equal 100 minus 93, which means what? Sigma is 7. Do you agree? You could even get that same answer even if you tried from this. Even if you tried 107 equal, as you can see here, 107 equal mu is 100 plus 1 sigma. 107 minus 100 is 7. 7 equals 1 sigma. Okay, so even from this, we get the answer. Okay, so just do one of the two things. You don't need to work with both. Okay, so we'll go to question number 6. The weights of a group of mice, sorry, we are not done yet, right? They're asking us to find what? They're asking us to find sigma square. So guys, if sigma is 7, sigma square will be 7 square. So sigma square is 49. So that's the final answer you're supposed to give for question number 5. Sigma square is 49. Is that clear? Okay, so moving on to question number 6, they say the weights of a group of mice, D grams, are modeled as D follows a normal distribution with mean mu and variance 25. Now remember this notation, the first one is mu, the second one is the sigma square. So remember 25 is the sigma square. Okay, if 97.5% of the mice weigh less than 70 grams, find mu. I think you might be wondering where did we get 97.5, because we've been working with 68%. We've been working with 95%. But where did we get 97.5%? Okay, so they have told us that it's best to draw the normal distribution here to understand. Okay. So when you draw the normal distribution, okay, so let's draw a bell-shaped graph. Okay, so this is the mean. The mean is unknown. Okay, and they are saying 97.5% of the mice weigh less than 70 grams. By now, you know that on either side of the mean, you have 50% of data, right? So if they say that 97.5% of the mice are going to weigh less than 70 grams, are you going to mark that 70 grams? Now, you know the area gives the probability, isn't it? The area gives the probability. So if the area here is 97.5. So 97.5% of the area needs to be covered by a weight less than 70. So where are you going to mark 70? Should I mark 70 behind the mu, or should I mark the 70 after mu? I want the area behind. 97.5% of the mice weigh less than. So if 97.5% of the mice weigh less than this 70, should I take 70 behind mu or after mu? Less than means from 70, you're supposed to go behind, backwards, right? This would be the area behind 70. Do you agree? So can this area represent the 97.5%? No, right? You can see it's even less than 50%. Therefore, the 70 can't be behind mu. So what does that tell you? That 70 should be, the 70 should be after the mu. Are you with me? So you have here the value of 70. And they say that 97.5% of the data okay, so 97.5% of data lies behind this 70. Are you with me? Can I know how much of data lies after 70? The percentage 100 minus 97.5, which is how much? 2.5. I think this should give you a small memory. So do you recall, because we did the questions where I gave you the, we found the area between within 1 standard deviation of the mean and area within 2 standard deviations of the mean. Am I correct? Okay. So then I think you can see over here, if you have the area within 1 standard deviation of the mean, the outside areas are 16%. Can you see? Do you recall this? And if you have the area within two standard deviations of the mean, I think you can see how much is the area outside. The area greater than mu plus 2 sigma, do you see it is? Can you see that this area is 2.5% on either side? Can you see the area greater than mu plus 2 sigma is 2.5% and the area behind mu plus 2 sigma is also 2.5%. Do you see this? So now I think you can understand that in front now. Now you saw in our graph also, in what we drew here, you had 2.5% of the data after 70, isn't it? So behind 70 or behind the mu plus 2 sigma, you have 95% plus the 2.5%. So 95 plus 2.5% is a 97.5%. So that's the full area here, the full amount. Do you guys agree with me? So 95% plus 2.5%, the total together here is 97.5. Okay, so which means that 70 here represents what? The 70 is falling over here and 70 represents mu plus 2 sigma. This is clear. The 70 will represent the mu plus 2 sigma. So you need to identify this. So mu is, so you can see here they have given D follows a normal distribution mean mu. And you know 25 is the sigma square. So what is sigma? If sigma square is 25, sigma is root 25, which is 5. So 70 equal mu plus 2 times sigma is 5. Mu plus 2 times 5, 10. So mu equals 70 minus 10, which is 60. So the mu value is 60. Is this clear? Okay. Okay, so next I'll move to question number 7. The masses of the sheep, capital M kilogram, on a farm are modeled as, you can see M follows a normal distribution, mean, mu, variance, sigma square. So this time both mu and sigma is not given to you. If 84% of the sheep weigh more than 52 kilogram and 97.5% of the sheep weigh more than 47.5 kilogram, find mu and sigma square. I think best thing we do here is let's draw two diagrams. Okay, so the first one is for weighing more than 52. So this is the mean and they are saying okay, so they are saying 84% of the sheep weigh more than 52 kilograms. So if it's 84% of the sheep weigh more than means which side do you need to go on here? So weighing more than means now here this is the mean weight. This mu is the mean weight. You know, behind mean, weighing less than the mean, you have 50% of the data. Weighing more than the mean, you have 50% of the data. So if I want 84% more than, okay, so there's a value 52 and 84% of the data points lie is greater than 52. Do I mark 52 behind the mu or do I mark 52 after the mu? Do I mark 52 over here or do I mark 52 to the right of mu, left of mu or right? The thing is, it's weighing more than, right? Not less than. Weighing more means from 52, more means you go to the front side. This is the more than side, right? And you can see this area, this is clearly, can this be a 84%? No, because you know exactly half the area is 50%. This is definitely lower than 50%, this area. So therefore, 52 must be what? Behind me. And this area that we're talking about, this area is actually what? This area is 84%. Guys, if this area is 84%, can I have the area behind this part? 16%. So if you refer back to the original diagram for mu plus 1 sigma and mu plus minus 1 sigma and mu plus minus 2 sigma, can you see the 16%? Yes. Can you see here? So you can see here 68 plus 16 is the 84%. So this 16% means what's the value we have over here? At this point, the value we have is mu minus 1 sigma. So that's what you have over here. 52 is what? 52 is mu minus 1 sigma. That's the equation number 1. Is this clear? Okay, let's get the other guy also now. So this is the mean mu. And they say here 97.5%. 97.5% of the sheep weigh more than 47.5 kilogram. How does that work? So again, they are saying weighing more than, which means what? From the line, you need to mark the greater than. You have to shape the greater than sign. So again, you need to realize definitely this 97.5% of the sheep weigh more than 47.5. So definitely 47.5 is even behind 52, isn't it? I mean, 52 was over here, so 47.5 should be further behind 52, isn't it? And then the area in front of 47.5, this area is 97.5%. Are you with me? Can I know the area behind? Over here, 100 minus 97.5 is 2.5. So guys, then what is this? 2.5%. Check in the previous diagram. So I have done this. As you can see 2.5% area comes for what? Here you can see the ends are becoming 2.5% when it is two standard deviations behind within the mean. So this is, since we are behind at this point, it's mu minus 2 sigma. The next equation you need to understand here is 47.5 is mu minus 2 sigma. That's equation number 2. You need to solve the two equations simultaneously and get the answer. Or you could substitute from one. I'll do substitution. So mu is 52 plus sigma. So substitute here. 47.5 equal mu is 52 plus sigma minus 2 sigma. 47.5 equals 52 plus sigma minus 2 sigma when we expand the bracket. So I get here 47.5 equals 52 minus sigma. Sigma equals 52 minus 47.5. How much is 52 minus 47.5? 52 minus 47.4.5. Okay, and then we are supposed to actually find what? Mu and sigma square. Okay, so first we have sigma. We're using sigma, let's find mu and then we'll go for sigma square. So then mu is equal to 52 plus sigma. Guys, get the answer. 52 plus 4.5. How much is it? 52 plus 4.5 is 56.5, right? So this is a weight. I think we are measuring the weights here. Yeah, it's everything's in kilograms. So 56.5 kilogram and sigma is 4.5. So sigma square is what they want. 4.5 square is how much? The square of 4.5 is 20.25. This is the variance of the weight, and this is the mean value. Okay, the mean weight. Okay, so I hope this exercise is clear to everyone now. So question number 7, I hope it's fully clear.